Have you ever considered that time could dilate, or that space could contract? Albert Einstein wasn't just a physicist, he was the man who changed our view of the universe. Today we'll discover how special relativity made us see that time and space aren't fixed, but relative, and how general relativity revealed that gravity isn't a force pulling us down, but a curvature in the fabric of space-time itself. Get ready for an amazing journey through Einstein's ideas that shattered the old rules of physics and launched a scientific revolution that continues to influence our lives today. Einstein's special relativity showed that space and time are relative. For example, in a scenario where lightning strikes both ends of a moving train, a person standing in the middle of the platform sees both lightning bolts simultaneously, while a passenger inside the moving train sees the flash ahead first because the train is moving toward them. General relativity revealed that gravity is not a force, but rather the curvature of space-time. Planets don't orbit the Sun because they are attracted by an invisible force, but because they move along the curved path of space-time caused by the Sun's mass. Einstein could have stopped there. He was already a legend. But he wanted more. He yearned for something deeper, a single elegant framework capable of explaining all the forces of nature. Gravity, electromagnetism, and even the strange new world of quantum mechanics, all woven together in a unified theory. Einstein began his search for that hidden unity when he was only 4 or 5 years old. One day, while bedridden and ill, his father handed him a compass. Einstein was fascinated by it. The steady motion of the needle spinning as if pulled by unseen hands left a profound and lasting impression on me. From that moment he believed that nature was governed by a hidden order. He believed in a God who is revealed in the harmony of all that exists. This became an obsession for him during the last 30 years of his life. Einstein began working on a unified field theory in the 1920s, attempting to unify the only two forces known at the time, gravity and electromagnetism. Electromagnetism is the force that unites electricity and magnetism. Moving electric charges create magnetic fields, and changing magnetic fields generate electric currents. Einstein could not accept the idea that they were unrelated. As he said in his Nobel Prize lecture, the mind that seeks unification cannot be satisfied with the existence of two completely independent fields in nature. He was overjoyed when the German mathematician Hermann Weyl showed signs of success in unifying the two fields. Based on Einstein's theory of general relativity, Weyl hoped to merge electromagnetism into a single entity. Weyl proposed a new kind of geometry for space-time, in which lengths could change as objects moved, influenced by electromagnetic fields. Imagine two identical measuring rods. If one were carried in a loop through the field and then returned, Weyl theorized it would contract or expand relative to the stationary rod as if it had remembered its journey. Despite his mathematical genius, Einstein even called it a stroke of genius of the first order. Nature doesn't work that way. In fact, the two rods would remain identical in length, and Einstein ultimately rejected Weyl's theory. Just a year later, in 1919, another bold proposal seemed promising. The German mathematician Theodor Kaluza suggested that our universe might have more dimensions than we realize. He introduced a fifth dimension beyond the four we know, 3 for space and 1 for time. In Kaluza's framework, the equations of general relativity unfolded in 4 dimensions, while the excess mathematics of the fifth dimension seeped into our 4-dimensional world as electric and magnetic fields. This idea intrigued Einstein, who said, "At first glance, I was very impressed by your idea." He even helped Kaluza publish his work in 1921 and then set about working on it independently. But there was a problem. If the fifth dimension really existed, why didn't we see it in our everyday lives? The Swedish theoretical physicist Oscar Klein offered an explanation. He proposed that the fifth dimension was real, but contained within a tiny circle, so small that it remained invisible. Imagine looking at a garden hose from a distance. From afar, it appears as a one-dimensional line. But as you get closer, you notice another direction, a circular dimension wrapping around it. Klein's refinement was a mathematical masterpiece, but it couldn't be proven. By reducing the fifth dimension to something compact and hidden, Klein gave the idea a flavour of quantum mechanics, the physics of very small objects that behave in ways that defy prediction. Take the electron, for example. It's not a tiny planet orbiting the Sun in a fixed path. Quantum mechanics reveals it as a cloud of probabilities. You can only predict the probability of it being in a particular region, never its precise trajectory. Then there's the double-slit experiment, one of the strangest experiments in science. If you fire photons or electrons at two slits, you might expect them to behave like bullets, creating two bands on the screen depending on which slit they pass through. Instead, they create an interference pattern because the particles behave like a wave, passing through both slits simultaneously and interfering with each other, even when the particles pass through one after the other. Then it gets even stranger. As soon as you set up a detector to measure which slit a particle passes through, the interference disappears. Suddenly, the photons or electrons behave like particles, producing only two bands. Just observing changes the result. Quantum theory deeply troubled Einstein. Concerned about randomness, he wrote to the physicist Max Born, "God does not play dice." He also joked with another colleague, "I look like an ostrich burying its head in the sands of relativity forever to avoid confronting the evil quantum mechanics." By the 1920s, physics had undergone a radical transformation thanks to the quantum mechanics revolution, led by young physicists such as Heisenberg, Schrödinger, and Dirac. Einstein acknowledged that quantum mechanics contained something of absolute truth, but insisted it was not the whole truth. For Einstein, only a unified field theory could offer a deeper and more complete explanation. Einstein refused to give up. In January 1929, he unveiled another version of his unified field theory. This time he resorted to what is called distant parallelism. This theory remained within the familiar four dimensions of space-time, but it added a special rule for how arrows or vectors could be aligned across extremely far apart points. The hope was that this new geometry would encompass both gravity and electromagnetism, all within the same space-time, without the need for a fifth dimension or a change in lengths. The press pounced on the theory. Einstein was already a global celebrity, and the idea that he had finally cracked the code of the universe dominated headlines. But physicists, like Wolfgang Pauli, were not impressed. Pauli called it too abstract. Beautiful mathematics, of course, but lacking a solid foundation in physical reality. He even joked with Einstein, predicting, "In a year, if not sooner, you'll give up on this distant parallel." The theory could not be proven. Einstein later admitted, "So I was right after all, you bastard." The search for unity became even more difficult with the emergence of new forces. In the 1930s, two new forces were discovered alongside gravity and electromagnetism. The strong nuclear force holds together the fundamental building blocks of atoms, the protons and neutrons. Without them, the positive charges of the protons would collide, tearing the nucleus apart. Neutrons also contribute to stability, acting as an additional glue in the bonding process. The strong force is incredibly powerful, about 100 times stronger than electromagnetism, and 100 trillion times stronger than gravity. If the strong force is what holds the nuclei of atoms together, the weak force is what allows them to change. Both protons and neutrons are made up of even smaller particles called quarks. 2 up quarks and 1 down quark for a proton, and 2 down quarks and 1 up quark for a neutron. The weak force can flip a quark from one type to another. It can turn a down quarky inside a neutron into an up quark, turn a neutron into a proton, and change its charge from neutral to positive. This is how our Sun works. The weak force drives the nuclear reactions it emits. The discovery of these two new forces led to more division rather than unity, making Einstein's quest even more difficult. However, in his later years, he made a final effort toward a unified theory. Einstein turned to an expanded version of the Riemannian scale, the mathematical tool at the heart of general relativity. In his new approach, the 10 components used to describe space-time were expanded to 16, in the hope of unifying gravity with electromagnetism, and perhaps even with other forces. But as with all his previous attempts, this effort remained unfinished and unproven. Frustrated, he confessed to an old friend, I'll never be able to solve it. His colleagues, such as Robert Oppenheimer, considered it futile. Oppenheimer declared bluntly, throughout his life, Einstein has done nothing good, insisting that he had strayed from the experimental foundations that had made him great, preoccupied with his fruitless quest for unity. On April 12, 1955, Einstein went to work at the Institute for Advanced Study, but complained of abdominal pain. The next day, he collapsed at home from a ruptured aortic aneurysm and was later taken to Princeton Hospital. Einstein refused surgery, content with his life as it was. He told his secretary, "There's no point in artificially prolonging life. I've done my duty, and it's time to go. I'll do my best." Despite his satisfaction with his achievements, he was prepared to die without fulfilling his ultimate dream. Yet even in his final moments, he couldn't abandon his pursuit. The day before his death, he asked for his last notebook so he could continue his quest. Shortly after 1 a.m. on April 18, 1955, an aneurysm ruptured. A nurse overheard him utter a few words in German, which she didn't understand. Einstein died at the age of 76. Beside his bed lay 12 pages of equations, his final attempt to understand unified field theory, which had consumed the last 3 decades of his life. Today, physicists continue to pursue the dream Einstein never realized. String theory, a promising unified theory, suggests that the fundamental building blocks of the universe are not point particles, but tiny strings of vibrating energy. The way the string vibrates determines the type of particle it will become. One might be an electron, another a quark, and yet another a graviton, the quantum carrier of gravity. In this framework, all particles and forces are unified as different expressions of the same fundamental thing, the string. Because strings have a finite length, they eliminate the problem of infinities that arises when using point particles to describe gravity on quantum scales. It is hoped that string theory will unify gravity, electromagnetism, and the strong and weak forces into a single, coherent framework. It is the holy grail of modern physics, a theory of everything. Curiosity was the driving force behind Einstein's entire life.